Hello and welcome to Say That Again Slowly, the Cambridge Festival podcast where students at Cambridge University chat with the experts who have contributed to the festival. We try to pair up students with researchers and authors from very different disciplines to bring things back to basics. There are no stupid questions here. My name is Onda Pledge. I'm a first-year undergraduate in the Faculty of English Literature, currently reading Shakespeare's comedies. Today, I'll be interviewing Luke Barnes and Geraint Lewis, who are the co-authors of The Cosmic Revolutionary's Handbook, or How to Beat the Big Bang, and A Fortunate Universe, Life in the Finely Tuned Cosmos.
Right. So to start this off gently, and at the very beginning, could you please explain in full why there is something rather than nothing?
Well, that's an easy question to start off with. Luke, do you want to kick off with this one? I mean, it's so easy.
Oh, how many hours have you got?
Yeah.
Look, opinions differ on this. My opinion on this is it's not fundamentally a scientific question. So science can explain how galaxies exist, for example, by explaining how they were assembled from other stuff. But that's just, if you then want to know why anything at all exists, the sort of explanation science gives of this stuff in terms of the other stuff just sends you around in a loop. So for me, it's either, that sort of question is not one that science can get at. So either it is answered beyond science or it doesn't have an answer at all. So there's been various people who've sort of defended both sides of that. Either there is no explanation for why. I mean, why is it the case that anything at all exists? So the people who say it doesn't need an answer. There's people who say there has to be something that exists in a different way to everything else, necessarily exists without needing a cause. It's the sort of thing that explains its own existence. Could be the universe, could be something else. But that's where we're at with that question. It's not really the sort of question that cosmology can answer, is my opinion.
Although there is an interesting scientific aspect to this question. So, of course, why does anything exist also brings in the concepts of space and time, etc. But we can ask a question about why there is stuff in the universe. That does become a scientific question. So, we're made of atoms, and we look out into the universe, we see there's trillions and trillions of stars, and they're all made of the same stuff. And it turns out that when we look at our equations of how the universe should have started, it should have started out in a reasonably perfect state, which meant there should have been equal amounts of matter and antimatter, and they get to a point in the universe where they should have annihilated and there should have been nothing left. So it turns out that something happened in the very early universe that made it slightly imperfect. So there was a breaking of the symmetries that we have somewhere that meant that there is matter in the universe, because without that matter, we wouldn't be here to have this conversation.
What do you mean by the breaking of the symmetry?
So it's again, how many hours do we have here? So symmetry is a concept at the core of physics. And what we mean by symmetry is that we have a set of equations and we do something to those equations and the results are the same. So one of the key ones is when we think about how do our laws of physics, say, change with time? And what we know is, of course, is that in our everyday experience, if I do a physics experiment today and I do a physics experiment tomorrow, I expect to get the same results. And it turns out that the conservation of energy is tied into that symmetry, that thing, the fact that it's the same today and tomorrow. And similarly, things to do with momentum are to do with whether or not I do my experiment here or there, or if I rotate my apparatus, etc. So whenever a physicist writes down some sort of fundamental equations, they look at this question of symmetries. What can I do to my equations to look at these symmetries? Because symmetries imply conservation laws, so things that are preserved in the universe. What we want, of course, is if we want more matter than antimatter, we've got to break that slightly. So we need to somehow ensure that the mathematical equations are essentially somewhat imbalanced, right? And so that processes that produce matter were very, very slightly more dominant than the processes that produce antimatter. And we don't really understand how that worked. I mean, this is something that's been bothering people for more than half a century. We know that something is somewhere in our fundamental understanding of the universe, there's got to be this break, but we can't quite pin it down.
So to go back to something that we sort of can pin down more, or is thought of as pinned down, if we go back to maybe the most rudimentary answer to the something rather than nothing question, which is the scientific Big Bang, could you give a brief explanation of what the Big Bang is for anyone who doesn't know?
Well, it's
over to you.
You hit it. All right.
No.
It's kind of two things, and this is where things get a bit tricky. There's an idea about the universe, which is just what was it structured like as we go backwards in time? What was the past of the universe like? And the Big Bang model is just in the past, the universe was hotter and denser. And so the further you go back, hotter and denser, hotter and denser, hotter and denser. Okay, that's the theory that we actually use day in and day out as cosmologists to do the work of explaining the observations around us. And it does a pretty remarkably good job. All of this happens in the context of Einstein's ideas about gravity and space-time. So all the mathematics of the model is there. But that's sort of the Big Bang as a model, as an idea about the past of the universe. But there's also this thing called the Big Bang as a point in the past, which is supposedly the sort of beginning of the universe. Now, the worry there is that all of the evidence we have at best points us back towards, earlier and earlier in time, but there's some point at which the evidence just runs out. If the universe gets hotter and hotter and hotter, at some point it's so hot that we've never seen matter that hot ever in any experiment. And if you go back even further, it's so hot that even our best theories can't even predict what would happen. The theories sort of run out of juice. If we take Einstein's ideas just as they are, they do predict fairly robustly some sort of beginning point under certain assumptions. But the worry is that the prediction that goes all the way to say this is a definite beginning, we've got some very, very interesting clues pointing in that direction, but all of our evidence and even our theories pull up short before we get to the Big Bang, meaning the beginning of the universe. So there's the scientific theory we can test with our observations in the past, the universe was hotter and denser. But then there's the Big Bang, which is as the beginning of time itself, which we have some clues pointing towards, but some big question marks as well.
But the evidence from Einstein's theory, is there a way to give a little insight into them, into what evidence that is?
So let me put it this way. If you take just Newton's ideas of gravity, so the older ideas of gravity, and you say, okay, well, we can invent a scenario and ask what the equations tell us is going to happen next. So make just a sphere of matter, perfectly, round, and then let it go. And it just collapses in on itself because gravity is attractive, and it all arrives at the center at exactly the same time. And that kind of looks like a weird singularity. Everything got infinite all of a sudden because everything arrived at the same point. In reality, you'd never actually be able to make a perfect sphere and things wouldn't pull exactly the same. So the thought was, okay, look, we've got this model of the universe. It's doing rather well. But as we push it back further in time in Einstein's equations, perhaps it will be the case that in a realistic model with bumps and lumps and things aren't exactly the same here and nothing's ever perfectly symmetric and all that sort of stuff, maybe we won't get a beginning point. What Stephen Hawking is famous for, and Roger Penrose as well, is a bunch of theorems, so a mathematical theorem, not a physical theory, that said that, well, actually, no, that's not going to save us. The way where you might think, okay, is that beginning point, is it real or not? Maybe it won't be in any realistic model. Actually, in actually most of the realistic models, it was there and it turned up. So that was Einstein's theory saying, actually, under fairly broad circumstances, something weird goes on here. The problem is, again, we don't think that Einstein's theory is the last word on what space and time do, because there's this whole other realm of physics called quantum mechanics. And those two theories aren't really talking to each other.
Perfect, thank you. So one piece of evidence for the Big Bang that you're saying veers away as soon as you get to it, but if we could just, I think that concept of veering away is really quite interesting. But so one of the pieces of evidence that's most commonly talked about, I think, is the redshift. The decrease of light frequency that suggests that things are getting further away, and so that they must have been at one point closer and all at one point. I'm sure you can explain that a little bit better than I can, but could you go into that and then maybe talk about how that veers away? Would that be possible?
Yeah, I'll do this one. So we can do a little bit of history first. We can go back to the 1920s and 30s, and so there was Einstein working with his equations, and there were also other theoreticians, Lemaitre and Friedman. But observationally, the name in the game here was Edwin Hubble, and he was using the world's largest telescope at the time, and he was interested in measuring the motions of galaxies. So we'd only just realized that there was more than just our Milky Way in the universe. So there'd been this big debate in the early 1920s about whether or not our Milky Way was the entire universe, or if our Milky Way was an island universe with other universes, island universes, which we now call galaxies out there. So people had finally conceded that there are other groups of stars. And the question was, how do they move amongst each other? Are they moving all in one direction, or are they buzzing around like bees, etc.? And it was known that you can use the Doppler shift to measure the motion of a galaxy, not the Doppler shift in sound, which we're quite used to, but the Doppler shift in light. And so if things are moving towards you, the frequencies increase, so things get blue shifted. Moving away from you, they get red shifted. And so Hubble was looking at galaxies. He was one of the first people to really do this. And what he found is that the nearest galaxies to us, especially the Andromeda galaxy, which is right next door, that's coming towards us, which is kind of what you expect. But he realized that the other galaxies were all red-shifted. They were all moving away from us. And you have to ask yourself, well, what does that mean? Does that imply that we are in a special place in the universe, and we've upset all the other galaxies and they want to get away from us? But what Lemaitre had shown is that if you take Einstein's equations and you accept that the universe is either expanding or contracting, okay? So Einstein struggled with this. Einstein thought we lived in a universe that was static and unchanging. So he messed around with his equations, and there's a whole nother story there, which has been told many times. But if you take Einstein's equations and say you populate the universe with other objects, these galaxies, and you have a universe which is expanding, then what would you expect to see? And you would expect to see, firstly, that galaxies would be moving away from you, and there would be a very tight relationship between how fast they are moving and how far away they are. So every time you double the distance, you double the speed. And when you look at Hubble's original diagram, which had a handful of galaxies on there, he draws a straight line through them, and you sort of go, well, is that really a good fit? But over the 100 years since, essentially now, we've measured the red shifts and distances to thousands upon thousands of galaxies, and we see this exceedingly precise relationship played out. So the galaxies are moving away from each other in the universe, and they're moving away in precisely the way that Lemaitre said they should in Einstein's picture. And the cool thing about when you go back and you look at Lemaitre's mathematics, you basically also point out that you can transpose yourself from one galaxy to another galaxy, and you see exactly the same thing. So any particular galaxy sees everybody else moving away. So we're not in a special place in the universe. We're just a galaxy, and we are, just part of this expanding universe. So that was one of the key results that demonstrate that we live in an expanding universe. There's been a lot of other bits of evidence that have come along since then. So Lemaitre was one of the first to say that we started in this fiery birth called the Big Bang. And there were some immediate predictions that if that was the case, how many ever billions of years ago, that there would be an imprint on the universe today of what happened in the first few minutes. And that imprint is firstly what's known as the primordial elements. So the universe was hot, so it was effectively a nuclear cooker, and it was turning hydrogen into helium, but that cooker basically ran out of steam very quickly in the first few minutes, and it could turn the universe into 75% hydrogen, 25% helium. When we look at the sun and ask what is the sun made of, it is 75% hydrogen, 25% helium. And all the other elements are basically, a trace. The other, which was a discovery in the 1960s, is this leftover radiation from the Big Bang. So it was a huge, immense fireball, okay? So as Luke mentioned, the temperatures were unimaginable, but as the universe has expanded, it has cooled. And so that has meant that matter has basically slowed down amongst itself. But also the radiation that was there, that used to be fiery hot, has got cooler and cooler and cooler. And it's still around today, and it's at around 3 degrees above absolute zero. And this was accidentally discovered in the 1960s, but has been studied to death over the last 50, 60 years with various satellites, etc., mapping out the details. And the only scientific theory that we have that includes the expansion, the primordial elements, this leftover radiation, and a few of the other tests that we have, is this Big Bang model, as we call it.
Okay, but thank you. So all these pieces of evidence, but you were saying, Luke, that they somewhat fall short, or they get close to it, or they suggest it, but they can't quite prove it. Am I right in thinking that that's what you were saying?
Well, again, there's the two ideas of the Big Bang. There's the physical theory of, in the past, the universe was hotter and denser. That's the one that does the hard work of actually explaining all the evidence that Geraint just talked about. If that's true, then we would expect galaxies to be redshifted. If that's true, we would expect nuclear reactions in the early universe to have a leftovers around us. If that's true, we would expect, to some extent, a cosmic microwave background. The thing that falls short of, the thing is, to make those predictions, the theory itself has to be valid back to some point backwards in time. So for the local galaxies, it's only got to be true for the last billion years or so. But the further back we go, which is a short amount of time if you're a cosmologist, the further back we go, the longer we need it to hold. So the cosmic microwave background, that background radiation needs to be sort of 400,000 years after the Big Bang. The nuclear reactions happen a couple of minutes after the Big Bang. But at no point do we need it to be true right at the point time equals zero, that instant of time. And in fact, these theories that we have in gravity and how matter works and what would happen if it was really hot and all that sort of stuff, those are working absolutely fine as we go backwards in time to give us the predictions we want. At some point really, really early on, a tiny fraction of a second, those theories just conk out on us. So it's not that we have sort of, it's like, if you went back in history, if you're sort of looking back into history through evidence of digging up layers of this, that, and the other, and at some point you just hit a rock bottom. The evidence we have is good to very early times. It's just, if you want to go back to that time equals zero, there was an absolute beginning, there's clues, but not the sort of evidence we have in support of the rest of that picture.
Can I just jump in and just clarify a little bit there? So the important thing to remember is that modern physics is built on two pillars, right? We have this one pillar, which is Einstein's general theory of relativity, which describes how gravity works. But there are three other fundamental forces in the universe. There's electromagnetism, and there's two nuclear forces, the strong and weak nuclear forces. But those three other forces, they are written in the language of quantum mechanics, which is a very different mathematical form to the mathematical form that we have in general relativity. When you get back to the very early universe, where you basically got all of the forces essentially vying for dominance in some sort of sense, what we really need is a mathematical framework with one language to describe everything. And that's what we're lacking. So there's a there's a theoretical wall that we haven't cracked that allows us to look back to time t equals 0. Now, this isn't a new problem because people have been trying to unify Einstein's idea of gravity with the other forces since 1916, basically, when the theory originally came out. Einstein on his deathbed was trying to work to meld gravity with electromagnetism. People are still trying to do it today. It's already a 100-year quest. And, it depends. You talk to some will tell you that we're getting closer. Others tell you that we're still half a century away. Others tell you that this idea that we can get this theory might even be a dream. But if we can find this theory of everything, as it's called, it's thought that would just pull back the curtain and reveal what happened at time equals 0. Was our universe truly born from nothing, or was it born from a previous universe, or some other complicated possibilities? But we are facing a theoretical challenge to sort of do that.
Great, thank you. Just to jump back a little bit to the redshift and how we're talking about how the universe is expanding from this supposed beginning. I stole this question, I think, from you in the Cosmic Revolutionary Handbook. But you asked the question of, so what then are we expanding into? How are we then creating more space as we go into it? Where are we going to if we are finite or in some way confined to begin with?
So,
yeah.
The idea of the Big Bang is the idea that space itself is expanding. So again, it's not that we sat down with some ideas and a couple of beers and some poets and thought, what's some wonderful stuff we can make up about the universe. Einstein had a theory about how gravity works. The most familiar thing around us, if I drop something, it falls. That idea involved space and time themselves being sort of part of the show rather than just being the backdrop to everything. That space and time themselves can twist and warp and be altered by the stuff that is in the space and time. The reason we go with that idea is it explains a whole lot of stuff extremely well. It's a wonderful scientific theory in terms of explaining the data, not just in terms of being a wacky sounding idea. Within that theory, when we try to explain the universe around us on the largest scale, the idea we have within that theory that best fits, the data that Geraint was talking about, is the idea of a universe in which there is literally more space as time goes on. Now, it gets a little bit weird if there's an infinitely large universe because you don't get more than infinity. But if the universe were finite, and there's a way of doing that without there being just an edge. So if the universe is finite, then it would literally be true that there is more space today than there was yesterday. You could fit, as Geraint told me many years ago, you can fit more oranges into the universe today than you could yesterday. So the idea is not of space is just there in the background. That's the older Newtonian idea. Einstein's idea is not just space just sits there and we're all just in it, but space itself expands. It's not expanding into anything, because if it expanded into something, that thing would have to be space. You can't have space expanding into space. That's a bit weird. So yeah, the idea of the Big Bang is the idea of an expanding space. Yes, there is more space today than there was yesterday.
Great, thank you. So moving on a little bit to the second of 3 points. Going to talk about black holes. So what on earth, excuse the pun, but what on earth is a black hole?
I'll have a go at this one. So again, we're going to have to go back to Einstein here, and we'll take it to about 1915, 1916, when he was putting the finishing touches to his general theory of relativity. And Einstein was famously good at his physics, but he always claimed that he was never very good at mathematics. And he had his equations and he looked at them and he just sort of went, oh, these equations are really hard. I don't think anybody will be able to solve the equations in that they will be able to write down analytic solutions. At the same time, of course, World War I was raging, and there was Karl Schwarzschild was a physicist who was serving on the Eastern Front, but he basically carried on his research and did mathematics almost recreationally, and he found the first analytic solution to Einstein's equations. And the solution that he found is a relatively straightforward one. What he wanted to know is, what does the gravitational field, the pull of gravity, look like outside of a spherical object? So you've got like the Earth or the Sun. What's the gravitational field look like outside? And of course, we know from Newton what we expect it to look like when gravity is weak. So we live in what's known as a weak gravitational regime. But once you get hold of Schwarzschild's equations, you can start to push the question harder. Right? Because what you can always do is you're talking about a sphere and it's got mass. So it's, it has a density. And so I can always keep the mass the same and I can make this sphere smaller. I can squeeze it so the density goes up. And you'd expect that the gravity near the surface will get larger because I've made the object denser. If you keep playing that game and squeezing and squeezing and squeezing, and let's take an object that we all know and love. Let's take the sun, right? Roughly 500,000 kilometers across, and let's squeeze it and squeeze it and squeeze it. So we keep squeezing down, right? So we squeeze it down. We can squeeze it down to the size of the Earth, and so the gravitational field is going to be immense, right? Because you've got the mass of the sun inside the volume of the Earth. Squeeze it down to the size of the moon. Keep squeezing and keep squeezing. And gravitational field goes up and up and up. Eventually, you start to get these effects which you don't get in Newtonian gravity, right? So that you start to feel the effects of curved space-time rather than it being Newtonian gravity. And then you've squeezed the sun and you've squeezed it down to a few kilometers, and you squeeze it down to within a ball of diameter 3 kilometers, okay? And you squeeze, and then suddenly when you hit that point, right, the gravity is so intense that the sun just completely collapses, okay? Gravity becomes the dominant force. Right? So when I'm squeezing, remember that it's like the pressure on the sun is pushing outwards, trying to resist my squeezing. I get it past that point, gravity wins, boom, the sun collapses down. And you ask inside Einstein's theory, where does that collapse stop? And it doesn't, right? The sun would just collapse and collapse and collapse and collapse and collapse until it has zero volume, okay? So what we have effectively done is we've created a black hole out of the sun, right? We have squeezed it down that it's got past this critical point where its gravity wins, nothing can support it, it collapses to a point. But it leaves this gravitational field around it. And that critical point that the sun passed, right, when the sun got past that point, it had to fall inwards. Everything that gets that close falls inwards. So you have your sun, all that mass in a volume, right, with no volume, right, zero volume, surrounded by this ghostly sphere. It's known as the Schwarzschild horizon, a diameter of around 3 kilometers. And that horizon is a one-way membrane. You can cross from outside to in, but once you're inside there, you can't get back out again. So that's what essentially what a black hole is. And what we've discovered is that in the universe, we have objects which are black holes, that they have all the signatures of being a black hole, from masses of a couple of times the mass of the sun to 30 to 40 times the mass of the sun. And in the middles of galaxies, we find them with millions to billions of times the mass of the sun. So there have been some really violent energetic events in the universe that have been able to compress mass down to such an extent that it completely collapses. So yeah, you can think of a black hole as a completely collapsed object with an intense gravitational field.
And thank you, that was great. And they're called black. So removal of light, can we talk about how the relationship to a black hole and how it affects light?
Yeah, so essentially, I mean, the concept is relatively simple, right? If you imagine that you've got a ball and you're outside and you throw the ball up in the air, you know, it's going to fall back down, right? So what's happening, of course, is when you throw the ball in the air, the ball starts off with speed, and as it climbs, gravity is pulling on it, and so gravity is robbing it of that speed until it stops and it falls back down. With light suffers the same kind of issue, except with light, when gravity acts on light, effectively what it's doing is it's robbing it of its energy. So if I'm here on the Earth and I've got a blue torch and I shine it upwards and the light rays travel upwards, they lose energy, and so they appear, the Earth's gravitational field isn't strong enough to do this, but let's just imagine it was, they would appear like they were red at the top, okay? So imagine that you've got your torch and you're going to go exploring a black hole. Okay, so you're very brave, firstly. I wouldn't want this job. But you're going to get closer and closer to this Schwarzschild horizon, and you're going to shine your torch outwards. And of course, what that means is that your light is having to climb out of a deeper and deeper gravitational potential, out of a deeper and deeper gravitational pull. So, you know, when you're far away from it, your light appears blue, but as you get closer, it goes into the red. And as you get closer and closer, it becomes infrared. And then the light that escapes is radio waves. And if you touch the horizon, that light loses all of its energy by the time it escapes. So effectively, what you've got is that horizon means that light that tries to set off from just the horizon itself can never escape. It's actually trapped there. If you were just below the horizon, so you're now inside that one-way membrane, the light's not going to get out anyway. Like, you're destined to be at the center, but then so is all the light. It all just gets pulled back and ends up at the center. So, I mean, one of the hand-wavy ways of describing a black hole is that it's an object whose gravitational field is so intense that not even light can escape. So, you know, it has that effect. Gravity is influencing the path of light.
So what would happen if you got close to one? I know that you couldn't really, but if we
you can.
Any idea? Can we? Okay.
Well, so firstly, right, I mean, the nearest black hole is a long way away, and we haven't traveled very far into space. So this is purely hypothetical. You have to find a nice black hole. Many black holes are surrounded by what's known as accretion disk. So this is matter moving at speeds close to the speed of light. It's intensely hot, glows with gamma rays and X-rays. You'd be fried. So you want to find a black hole that doesn't have any of that stuff. If you just fall in, okay, you would happily just fall. It would be like that you're falling here on the Earth. And I don't know if you've you know the feeling, like you're going along in a car and you go over a bridge and you get that feeling in your stomach, right? You know what, that free fall kind of feeling, right? Yeah, you would still have that. You'd be free falling, and actually, as you're free falling, you would happily sail through that horizon. Okay, you couldn't get back out again. You'd pass through. Now, exactly what's going to happen depends upon the size of the black hole, because what's going to happen is that the rate at which gravity is changing is going to get larger and larger. It's going to get faster and faster as you get closer. And what I mean by that is, imagine that you fall feet first, okay? So your feet go through the horizon first, then your shoulders, then your head, etc. As you get closer to the center, the gravitational pull on your feet is going to be much stronger than the gravitational pull on your head. Okay, and so what would happen is that your body would start to be stretched. So in fact, you have a force that's stretching you this way, and you actually have another force that's sort of squeezing you inwards from the side. So you would be drawn out longer and longer until, you know, basically your sinews and eventually your atoms can't hold you together. So this is a process which physicists call spaghettification. because you get drawn out into effectively a long, thin string, and then, but then you end up at the center of the black hole anyway.
So would you be ripped apart?
Yes.
Yeah.
Now, there's an interesting question here, which I've talked to people about, and I do not know the answer, right? Is because your nerve signals actually travel quite slowly. So, your nerve signals, I think, travel like 30 kilometers per hour or second. No, one of that sounds, anyway, nerve signals are much slower than the speed of light. So the whole point, the question is that if, as you get torn apart, does your brain really know about it? Do the signals travel faster? And it's too messy a picture. Nobody really wants to talk about it. So we'll leave that one as a bit of mystery. But yeah, you would end up being shredded.
Right. Now on to time travel. Is there a possibility of time travel? When you Google it, it says it is possible, but I mean, I'm not sure how much I believe in Doctor Who.
So the short story is, and this is the running theme, is that, I mean, we need a theory of space and time to tell us whether it's possible. Obviously, it hasn't happened yet. So, and the best theory of space and time we have again is Einstein. And Einstein's theory says, yes, it is possible. This was not known for the longest time. So Einstein first formulated fully his idea of his theory, general relativity, as it's called, in 1915. And then I believe it was 1951, there was a conference in his honor, and a very eccentric mathematical friend of his called Kurt Gödel turned up with a solution to Einstein's equations in which there was time travel, in which you could go on a certain path in a certain space-time, a certain universe. You could go on a path, and when you got back around, you would meet not just yourself at the same place that you left from, but the same place and time. You could get back to that same event again. So the way this is often put is you could play poker against yourself. Beyond that, it was later discovered, actually, the weird thing that these space-times seem to have in common is rotation. The universe as a whole rotates and weird stuff starts to happen. Gödel's universe was a rotating universe. It was discovered that actually inside a rotating black hole, you can go and play poker with yourself as well. The singularity, the point you get ripped apart, actually becomes a ring. And if you hit things just right, you'll go through the ring and around a few times and start playing poker with yourself. The worry, all the classical time travel worries about the grandfather paradox. What if my time machine lands on top of my own grandfather before my father is born, and then, I don't exist, and then I've gone around again? All of that is not sort of automatically erased. So we don't know whether, how those two things would sort of interact with each other, the logical troubles. But if there was time travel, it would have to be the case somehow that obviously there can't be a logical contradiction. So again, we don't have a complete and final theory that puts gravity and quantum mechanics and all of that together. But at least within Einstein's theory, the answer is yes, it is possible. The question then is, what would we actually have to do to space and time themselves? Is there anything we can do, boil the right thing at the right temperature and throw in some magnets or whatever, spin them around? Is there anything we can actually do to make time travel happen? And the answer is not as far as we know. You'd have to go find yourself a spinning black hole. But at least in terms of possibilities, it is there.
Is there a I did a tiny bit of reading about this, but so is there a theory or evidence that the stronger that gravity is, the more that has an effect on time?
Yeah.
So the problem is traveling into the past. That's the problem. We can easily time travel into the future. We know how to do that one
at different rates.
At different rates, yeah. So again, you mentioned about going near a black hole, and we already said, no, there's this effect about light escaping. But one of the other things is that clock rates are different depending upon the strength of gravity. So if we take take you and we pop you near the event horizon, not inside, just outside, and we just leave you there. Then the clock on your wrist and all of your internal bodily clocks and all those kind of things will tick slow relative to the clocks in the universe. So if you go down there and you sit there for a bit and you come out, you may have aged a year, but 10,000 years may have passed in the universe around you. So traveling into the future is the easy one. So we definitely know how to do that. It's the traveling into the past is the tricky one.
So traveling into the future, is that just gravity then, or is that is there other elements that come into that?
Well, as Luke mentioned, if you want to mess around, the only theory that we have where time is malleable is general relativity. So in quantum mechanics, time still ticks like a regular kind of clock-ish. There are some subtleties there, but if you really want to bend and stretch time, it's Einstein's relativity, and it's implicitly tied to gravity. Now, the way you bend space and time is related to how you arrange your mass and energy. And as Luke mentioned, one way you could arrange it is in a spinning black hole. That gives you time travel possibilities. There is actually another possibility, which is what's known as a wormhole, which is essentially where you dig a tunnel from one point in space and time to another point in space and time. And again, we can write out the mathematical equations to describe that space-time structure. But we don't know if we can ever arrange matter and energy in the right way to do it. So yeah, they are in theory, right? They are possible, but we are stuck with this issue that we can't rule them out because we don't know what's physically implausible, because the universe is a very strange place. There's a lot of weird stuff that goes on.
So we know that it can happen, but we don't know, am I right in thinking that we have not yet done it ourselves or like manufactured it?
Oh, actually, well, we have done it in the sense that we've done experiments that directly have measured time travel. So there was a famous experiment from the 1970s, I think it was, might be, which I think is before your time, isn't it? Yeah.
It's before my time.
So it's not before my time, unfortunately. Where essentially what they did is they took two atomic clocks and they put them on different aircraft and they flew them around the world in different directions, right? So those clocks were experiencing different gravitational fields and different actions of gravity because they were going in different directions with regards to the Earth's spin. They brought the clocks back together and the clocks were out of sync. So the clocks had time traveled relative to one another. One clock was younger than the other clock. And in fact, I believe it was only maybe this year or even last year, they did an experiment in a laboratory where they measured effectively the time travel difference over the separation of like a millimeter. I think that was right. So we know it's there. We can measure it. But of course, on that kind of scale and in the Earth's gravitational field, you are talking about millionths and billionths of a second. That's the differences that you can make. If you really want to time travel, you want 10,000 years to pass over here when you just spend a year over here. So we just don't have the strength of gravitational field that allows us to do that kind of thing.
We can definitely measure it, but we can't perhaps artificially induce it. We can't, let's say, create a blue box that we can walk into and then walk out of and be in the future.
I'm going to say yet, because I mean, look, building a blue box, that's an engineering problem, right? We know the physics, right? So it's not just the box. We do have to work out how to manipulate space and time, and you do that by manipulating mass and energy. And there are science fiction stories where people essentially build suns and black holes. They do stellar engineering, but we are currently a long way from doing that.
Great, thank you. So we've touched on the three big topics that were in the title of this episode, but are there any other parts of space that you think are missed out usually when we talk about cosmology? Or anything you find particularly interesting that you would like to just spend 5 minutes talking about?
Okay, I'll talk about. I'm going to go first, Luke. So one of the aspects of my research, I mean, I study lots of stuff to do with the universe, light traveling through the universe, that kind of stuff. But one of the areas of research I'm doing at the moment is something called galactic cannibalism, and that's a really interesting topic because when we look at our Milky Way galaxy, where our sun's home in the universe, there are roughly 200 billion stars in it. But we know that our galaxy has grown over time, right? It started off small and it's gotten bigger. And of course, it's gotten bigger by essentially consuming other objects. So as little galaxies have gotten too close, the gravity of our own Milky Way has grabbed onto them, torn them apart, and their stars get added to the stars in the Milky Way. And what's really cool is like over the last now 20 to 30 years, we've realized that this feeding of the Milky Way has not ended. It's still going on. And what we're doing is we're finding more and more evidence of what the Milky Way snacked on in the past over the last 5 to 10 billion years, what is eating right now, and it is consuming lots of little things. We look into the outer reaches of our Milky Way galaxy, and we see all these basically shreds of galaxies that are being torn apart. And then if we look slightly further, we see that we are surrounded by, in the local universe, between 50 and 100 other little dwarf galaxies. That's like a larder, right? That's food yet to come. So that's one thing I think that doesn't get a lot of limelight in the discussions of the universe. But I think that action of how our home in the universe has grown over time, I think is a pretty cool one. So that was my sort of 2-minute summary.
Great, that's really interesting. That consumption that you're talking about, what does that look like? How like what? I mean, I assume it's not actual eating. So what does that?
I was thinking, Geraint, you could call it galactic recruitment. You're just getting other stars.
Yeah, sort of. So if you imagine that we've got a little galaxy, so a little galaxy might have a few 100 million, maybe 1 billion stars in it, but they're all held together by their own gravity, right? So they all are happily traveling through the universe together. And they arrive close to the Milky Way, and the gravity of the Milky Way starts to pull on them. And what that does is starts to stretch it out. Okay, so gravity is pulling and pulling, a bit like that spaghettification, and pulls them and pulls them and pulls them. And eventually what happens is that the stars that were feeling each other's gravity, that's how they were staying together, they lose touch with each other. They basically forget that they were part of a single object. So these stars are now effectively loose. And their orbit, where they go, their future, is now completely dictated by the gravitational pull of our Milky Way galaxy. So those stars just get added to the stars of our own, and they completely forget the parent galaxy from which they came. So yeah, so it's when you ask what we can see, again, it's one of those things. You wish you had eyes which were 8 meters across, because you would be a sensitive telescope and you could see so much more in the universe. What we'd see is that our sky would be crisscrossed with these streams of stars, right? We can see these things being dismembered right now, and they would be up there on the sky. And if we waited a few billion years, we would see them being steadily dismembered, and eventually they would basically disappear into the background. So, this cannibalism is this ongoing thing, which we realize, we can now see and we can now measure.
Thank you. Luke, is there anything that you think is overlooked?
No, how long have we got? Let me give a quick one. Actually, Geraint and I and a student of his were talking about this earlier today, and I've been thinking about it a lot because I'm preparing lectures that include the second law of thermodynamics, which is one of very famous things. You mentioned Shakespeare before. There's a famous essay called The Two Cultures about sort of humanities and science coming together. And there's the writer says that the question, what is the second law of thermodynamics, is up there with have you read a work of Shakespeare's? That those are the sort of crucially important questions. And the sort of moral of the story at the end of the day with the second law is that we think of it as disorder is increasing, and so the universe is headed towards a heat death. So it's all slowing down, and the forms of energy, a more precise way of saying that is perhaps the forms of energy around us are becoming less and less useful. It's becoming harder and harder to turn one form of energy into another form to have it do something interesting for you. But the consequence of that, if you turn it around and run it backwards in time, is that the beginning of the universe has loads and loads of useful energy. And that's only the case if there's something rather peculiar or rare or unusual about the way that the universe started. So there's this picture of the Big Bang as just being some random explosion that sent stuff in all directions. Actually, the picture we have to have of the beginning of the universe has to be one in which, in some way or another, and this is part of what the paper was about, there's something about the way the energy is arranged, the stuff of the universe is arranged, that means that there is a lot of useful energy in a world in which, quite naturally, the second law, that all those forms of energy degrade, and so the most likely state of any of stuff in the universe is useless. So to have a useful beginning of the universe, this is called the past hypothesis, I think is something that actually, even amongst cosmologists, doesn't get enough in recognition and thought, and especially and beyond that, even into the public. It just means that the story of the universe is not the story of order coming out of chaos. It's complexity coming out of order. It's things started off in a special ordered state and then got more complex as you got, planets and animals and all that sort of stuff. But the order was there from the beginning, if there was a beginning.
That seems like a perfect place to start. Thank you very much for speaking to us, well, to me, but to Cambridge today. Make sure to follow the Cambridge Festival on Facebook, Twitter, Instagram, and YouTube for more fascinating events, and follow the Say That Again Slowly podcast for more conversations with experts on body image, aliens, counterfeit, and much more. Thanks for listening.